Hello and welcome to our second machine learning example. In this example, we'll try to detect bullying messages from social media comments. In other words, people are posting something to social media, other people are responding, and we are trying to automatically detect messages that can be classified as aggressive, messages intended to insult somebody, to put somebody off balance, and things like that. So those are those type of messages typically fall under the umbrella of cyberbullying or simply bullying. Just like we did in our previous example, we will use the Caret package. This is just one of the packages that comprise R collection, CRAN collection for R. This package contains many machine learning algorithm implemented. And just like we did last time, we will use the text mining or TM package in conjunction with the Caret package to pre-process our messages, our documents, to convert them into a document term matrix. If you don't have these two packages installed, then I suggest you pause the video and install them before proceeding. And then once you install them, use the library command to load them, or simply go to the packages tab in RStudio and check the packages that you wish to load. So once again, if you don't have those packages installed, then pause this video and install them before proceeding. Running this example requires a data file called boolean dataset CSV. It's a comma separated value. I saved this file into a folder which is a subfolder for this class. So this is the path to which I'm setting my working directory. In your case, it will be different, obviously. It will depend where you save your file. Just remember to use forward slashes, because otherwise the system will give you an error message. So let me show you briefly what this data file contains. So here in this data file, we have only two columns. The first column contains cases. Those are the messages that people post on social media. And the second column contains our dependent variable, classification variable, bully or not. So 0 means it's not a bullying message, 1 means it is a bullying message. To be honest, I'm not sure about the exact nature of this data set. I think it was downloaded somewhere from the web. I think it was something done by humans. In other words, humans looked at 40,000 messages posted to social media and classified them manually into bullying versus non-bullying. I think 3 raters were involved. So 3 people would rate those messages. So in case there's a disagreement, there will be like a decision rule. Let's say if one person says that it's a bullying message, but 2 other raters say that it's not a bullying message, then it's a 0. If 2 raters say it's a bullying message while 1 person says it's not, then the message is classified as a bullying message, because majority, meaning 2 out of 3 raters, voted for this message to be a bullying. And I apologize, if you look through all those messages, you will see that some of the bullying messages contain profane language. So that would be your guess, right? That bullying messages usually use bad, foul language, and that's probably how they are detected eventually. So take a look at this data set. One thing I would like to note is that here we have almost 41,000 messages, and this is something that will push the limits of your computer machine. At least my machine, it's not that powerful. I think I have 16 gigs of RAM. And it all comes down to RAM, mostly comes down to RAM because R does processing in memory. So it's RStudio, R language is a part of that in-memory analytics paradigm where data is loaded into RAM. And for text mining, things can quickly get out of control if you don't have enough RAM. Now there are workarounds. Usually what I do, when I do text mining exercises, be it something related to machine learning or simply topic mining or text summary or word cloud summary, something like that, I usually limit the number of documents or messages that I have. Just to give you a rule of thumb, my computer seems to handle well data sets that contain up to 10,000 messages, like 10,000 tweets. To be safe, I would use something closer to 5,000. So what's the solution to this big data problem where you have 40,000 messages and your computer is not powerful enough to analyze all of them? Well, In that case, you will have to take a subset. So that's a very simple brute force solution to the big data problem. Instead of analyzing the entire data set, analyze a small subset, okay? And we'll do it partially, like we'll use a small training data set. We will do the prediction, on a subset of this data. So we're not going to deal with 40,000 observations because it's something that will push the limits of my computer. Most likely it will freeze because it will run out of RAM at some point. So this is just a word of caution. And even this subsample takes quite a bit to analyze. So what I will do, I'll pause my video and wait until RStudio gives me an output. So what I'm trying to say is that as we go through this example, if your computer is not that powerful, then maybe change numbers. Use smaller training set and smaller data set for making actual predictions. So this is what this data contains. So once again, make sure your working directory is pointing to the correct folder where the data is located. I will go ahead and read that Boolean data. So next, now we have this Boolean data into a data frame. We'll load it into a data frame. So now what we will do, we'll generate a training set. So we'll have a subset of 100 numbers. So from those 40,000, almost 41,000 observations, we'll take a random sample of 100 observations. Now those numbers will come from a uniform distribution. In other words, we want to make sure that every case, every observation in our data set has an equal chance of being selected. We set a seed to make sure that it's reproducible so that the indices that we generate for selecting the subset are the same each time we run the script. If you don't have that set seed command, then the output will be different each time you run this code. So we'll set the seed and then we'll generate indices, which means 100 numbers from 1 to 40,952. So that's the number of cases that we have. Again, we are trying to generate a subset of 100 messages that will be used in training. So we generate those indices, then we use the square brackets notation to actually save the messages that correspond to those indices that we randomly generated into a new data frame. So that will be our training data frame or training set. We will only save cases from the training set. Yeah, we'll just do it for now. For now, we'll be dealing with text only, so we'll save it into a corpus variable. So using the vcorpus function, we'll convert this data. So right now, this data, as you can see, contains only those messages. We'll convert it into a corpus, and then we'll create a document term matrix based on this corpus, and we'll do the usual pre-processing. We'll remove punctuation, stop words, we'll do stemming, and we'll remove numbers. So now this variable TDM contains our document term matrix. Again, in order for this document term matrix to be usable by Caret package, we need to convert it into a matrix and then the data frame. So once it's converted into matrix, you will get a sense of what it contains. Sorry. So you see it's a huge table that contains terms as columns, and then you have values for each document. So in our case, we have 100 documents. And then what we'll do, we'll attach another column here. Remember, there is a Boolean or not column where each message is classified into a Boolean versus non-Boolean. So from that subset, we'll cbind, we'll append another column that will contain the classification for each of the messages, meaning zeros and ones with its Boolean or not. And then we'll rename this Boolean or not column into Y, because that's our predictor or classification variable. Not the predictor, the variable that we're trying to predict. And then we'll convert this matrix into a data frame, and we'll save it into another data frame called train. And as we did last time, we'll make sure that variable y is converted to factors, because that's what needed for Caret package. So what we'll do next, we'll go ahead using the subset, we'll go ahead and train the Bayes GLM algorithm. We talked about this algorithm briefly, which is similar to logistics regression. We'll train it to predict outcome variable y, meaning whether the dataset is Boolean or not, based on all. Well, in our case, we're talking about based on all words, all terms that are contained in that document term matrix. So the data will be trained. So we'll go ahead and train. So I'll run this line of code, and it will run for a while. I think on my machine it runs for like 1 minute. So what I will do, I will just... So yeah, I paused the video because it takes my computer approximately between 1 and 2 minutes to train the algorithm using the training set containing only 100 documents. So if you use something more than that, I'm afraid it will take you exponentially more time. So it's not going to... So for example, if you make a data set of 1000, training this data set of 1000, I suspect it will take you much longer than 1 minute. But nevertheless, we're done now, so I skipped that part. So the train model is now in that fit object, which is a list. Okay, so what we'll do, we'll check the accuracy of training. So we'll try to use the same data set that we used for training for predicting whether a message is Boolean or not. And we get the same kind. I mean, I'm not going to match it right now, but we get the same kind of output because, again, we use this data set for training. So now what we'll do, we'll generate a new test. We'll see how well our trained model is at predicting Boolean messages, classifying messages as Boolean in a new data set. But again, we'll get this new data set from the same subset. We'll use a uniform distribution to draw a random sample of 1000 messages. We're gonna do the same thing. We'll use those indices. We'll use the square brackets notation to get that subset. So we'll save in data2 variable only cases, meaning only text of those 1000 messages. Then we'll convert it into a corpus, and then we'll convert this corpus into a document term matrix as we did before. And then we'll convert this TDM object, which is a list, into a matrix. And then we're gonna save the output of the prediction output, again using the model that we already trained, which is contained in that fit object. But the new data, the data that will come into this predict function will be our new data set, which has 1000 observations drawn from our original data set. So we'll save the output in that predicted variable. So now we're gonna display results. So what we will do, we'll have a variable called result, and what we will do, we will actually match whatever we predicted to the actual content. Okay. So remember, we have our test set, the set that contains 1000 observations, and we'll use the Boolean or not, meaning that y variable. So here we have zeros and ones, and we're gonna match it one by one, case by case, against what we predicted using the model that we generated based on the training set. So for every number, what it will do, for every case, for every observation, what it will do, it will compare what we predicted, meaning 0, 1, Boolean or not, versus what was the actual classification by humans. Okay, and then we'll save everything into the result variable, and then we'll generate output table based on that. So this is what's contained in output table. So output table tells us how many predictions were false and how many predictions were true. And this is what you see in the result variable. A bunch of false and true. So we get false when there's no match between the actual classification and what we predicted, and we get true when there is a match. So we calculate accuracy by dividing the number of predictors that were true by 1000. So the accuracy is roughly 90%. So that's not bad. So we were able to predict, to make a correct classification in roughly 90% of cases. There may be a better way to generate this table. There are some general tables that are used in machine learning for for detecting false positives, and things like that. So there may be a better way to generate a table to see how accurate our trained model is. But for now, I'll just stick to this simple example where I show you that we trained our model, we try to predict, and we get a fairly accurate prediction based on the model that we have trained. So that concludes our second machine learning example. Thank you for watching.